Hi again. Today we're talking about organic reactions, and it's going to be a quick little video just to get the whole concept introduced. I know that since you've taken at least 1 year of chemistry, you know a little bit about reactions. Organic reactions, it's not that they're so different, but we present them differently. And a lot of those really important rules that you had for reactions before, we tend to ignore. Let's just be honest. So, first of all, what does it mean when we talk about an organic reaction? Well, the number one thing is that it's converting from one functional group to a different functional group. So we tend to focus on those functional groups. We tend to organize our reactions according to how they change the functional group. So we'll end up with a lot more terminology in this section than you would have had in, say, a previous course where you maybe had 5 kinds of reactions or something like that, synthesis and displacements and so on. We tend to emphasize the organic part of it, and what that means, I'll show you an example in a minute. What that means is when we write out the reactants, we tend to write the organic reactant in that reactant spot, and we tend to write the organic product as the product spot, and then some of the other stuff either gets written on the arrow or ignored altogether, and I'll show you examples of that in a minute. And we also never balance organic reactions. It's possible to do so, we just don't bother. And again, I'll show you some examples and try and make that clear. And the reason for it is because we aren't so interested in, let's say, the stoichiometry of it, right? Balancing reactions came out of this law of conservation of mass kind of thing where we had to account for all the atoms. Now, that's less important to us. What's more important is that we know what's the functional group we started with, what's the functional group that we finish with. So here's an example of an organic reaction in A, how it's written, and B, how we emphasize the organic pieces and de-emphasize the non-organic pieces, and also how we don't worry about balancing. So on the far left, we have an alkyne. And what we're doing is we're taking hydrogen and we're adding it across the double bonds. In other words, we're taking an unsaturated hydrocarbon and we're saturating it. Now, you'd never do this reaction that way because it'd be a total waste of money, but that's not the point. It's possible. But you'll notice that if I look at the product, I only have one product written down, and I don't have it balanced. If I start doing a count of hydrogen, I've actually added 4 hydrogen atoms or 2 hydrogen molecules to my original reactant, which means it's not balanced. But that's okay. The way this reaction would actually happen is I would start out with the organic reactant and I would just bubble in hydrogen gas, and I would just turn on that tap and let it run for 10, 15, 20 minutes, something like that. And I'd come back to it later. And I would never bother to measure the hydrogen gas. The PT, that's platinum, that's going to act as a catalyst. And you'll notice that the hydrogen, as the other reactant, and the platinum, the catalyst, are written on the arrow or below the arrow, and they are considered or spoken of more as the reaction conditions rather than anything else. Okay, now we get into the terminology. And we're actually going to group our reactions according to some of these terms. There's elimination reactions, and elimination reactions are actually, I think, pretty obvious in terms of the name. What they are is something is being removed. Now, we have to keep in mind that if I'm going to take something away, if I'm going to eliminate something, I still have to follow my cardinal rule of organic chemistry. Every carbon has 4 bonds, no more, no less, no exceptions. So it's very rare that I only have to eliminate one thing. If I'm going to break a bond, I have to replace it somewhere. So in this one, I'm taking out not only the OH, right, and that's an important thing to notice, and that's probably the first thing you noticed, but I'm also taking the H, hydrogen, from a carbon that is beside. So that's important, so that if I took away the OH from the carbon that had it, it's down to 3 bonds. Can't have that. So I lose a hydrogen from next door, and now I can form my 4th bond to that carbon. Again, the reaction conditions are given there. We'll go through these reactions in a little bit more detail, but that is H2SO4, sulfuric acid, conch. It has nothing to do with Lord of the Flies, that's concentrated. It's just the arrow's too short to write the whole thing. We have substitution reactions. One thing taken out, one thing put in. And in that case, the example I'm giving you is given here, where the OH is taken out and a Cl is put in. So I've gone from an alcohol functional group to an alkyl halide. You'll notice again that I'm not accounting for where that OH went, and I'm also not accounting for what happened to the rest of the phosphorus pentachloride, because I don't care. I want to know what organic product comes out, that's on this side, and I need to know what organic product goes in. And I guess for you it's the other way around, but for me this is the, yeah. Oxidation. Oxidation is something that is a term that we're going to see a lot of times, and I'm going to give you sort of a whole range of things. And oxidation can start anywhere almost on that chain and move that way, move further toward the oxidation side of things. So oxidation, in simplest terms for organic chemistry, is just how many bonds to oxygen do I have? So I started out with no bonds to oxygen, then I moved to one bond to oxygen. So going from an alkane, or an alkene I suppose, to an alcohol. Now I go to 2 bonds to an oxygen. This is an aldehyde, but it could also be a ketone. I move to 3 bonds to oxygen, a carboxylic acid. Now ultimately, the most oxidized I could have is 4 bonds to oxygen, which is carbon dioxide. From an organic chemistry point of view, that's not very helpful. So normally I'm working with moving between alcohol to the carbon-oxygen double bond to the carboxylic acid. And I guess again I'm going the wrong way. But moving within those middle 3. I can also, in some reactions, move backwards that way. So I can go from more bonds to oxygen to fewer bonds to oxygen, and that's called a reduction. Now, by the way, a little later in this course, we're going to have the terms oxidation and reduction again, and they'll mean something a little bit more properly defined. So for us right now in organic chemistry, which is kind of loosey-goosey and stuff, those terms will work. And then finally, there's addition reactions. And addition reactions are very much what they sound like. Something's being added. Well, I need a place to add them too, so I almost always start out with a carbon-carbon double bond or a carbon-carbon triple bond. And then something gets added across the double bond. And that's really key because both carbons of that double bond need to have something added to it. Although, there's usually only one carbon of the double bond that I really pay attention to, because it's often hydrogen and something else. So I see the something else showing up in the product, but not so much other things. Some reactions actually show some preference. If I look at a reaction here, if I'm an addition reaction, elimination reactions will as well, I actually have 2 options for how I can add a hydrogen chloride across the double bond. I can add it in the way you see here, hydrogen and chlorine, or I can add it the other way around, turn that hydrogen chloride molecule around. We'll get into the details and why and how do we predict in class, but for the short story right now, the bottom one would be preferred. Now what do I mean by preferred? Maybe it's 80% will go this direction, maybe it's 90%. It kind of depends from reaction to reaction. We're not going to need to know how much it's preferred. Our job is going to be to recognize that I've got more than one option, which one is preferred. It may or may not be helpful to think about how these things happen, how the electrons move around, how the bonds change out. So I'm going to start with an addition reaction. And in an addition reaction, I'm using the electrons of that carbon-carbon double bond, or at least one of the bonds. There's 2 to work with. And I'm going to add a hydrogen bromide. Now I've got it written backwards because that's the preference. The electrons move from being shared between hydrogen and bromine and between that carbon and carbon to now being shared between all the other ones. And if you follow the arrows, that's where they're going. Now, why do I have 4 arrows? Because I have 4 electrons. So every bond is 2 electrons. So I'm trying to account for every electron. That then breaks the bond the two bonds that were existing forms two new bonds. Keep a track of that symmetric math, hey? Because that's going to happen. If I break two bonds, I'll form two bonds. If I form two bonds, or if I, whatever. If I need two bonds, it'll all work out. And then I form that compound, which of course I'm not going to write like that. I'm going to write more like this, as we see here. It's actually not that big of a deal. What's important though is we start to follow how this thing works, and we start to sort out in our minds the different kinds of reactions, and really focusing on functional groups, going from one functional group to another functional group. I sometimes hear people talking about that this reaction changes the OH into a Cl. Well, there's no magic. It's bonds had to break and bonds had to form. So if we kind of keep that in focus, then we should be in pretty good shape. But we'll do lots of examples in class, and we'll see you then.